so bad compared to the teachers at the school or the middle school, even high school, because for whatever the teachers will be, and then they always can memorize the student's name just in the first week of the class, right? And they're so great, but I couldn't. I promise when next for the test too, I will call the name and then to take your sheet, and then I will try to remember the face, match the face and name. Okay, so here that is 2500. Up to here, any questions? And this is the about the geometry, and this is what we call the compatibility for the gear set problems. Okay. So now we can begin to do the checking the criteria. So we design to meet the criteria, the maximum less than 60 MPa. So we check against the first one. So the maximum stress, because both shafts are the same in diameters. So here we take is the maximum, the tau maximum equal to TC over J, and C or J, they are the same for the both shafts. So we pick where they have the larger T for calculation. So that should be go to the shaft AB, and this one less than 60 MPa. Okay, so here we, therefore, based upon the reasoning, because the both shafts have the same diameters, so we pick the whatever the T is larger, which is shaft AB, is chosen for checking. Okay, so that means 25 times C divided by pi over 2 C to the fourth power less than this one MPa. So using this criteria, we can see C must be greater than or equal to 29.8 millimeters. So that is the first result we obtained. Then we, the second one to meet.
Why did you switch the sign?
Oh yes, why I switched the sign? And yes, let me do this one here. So for this case, that is 25 by pi over 2 times C to the 2, right?
Yeah.
And less than 60 times 10 to the 6 PA. So here you can see 25 divided by 60, yes. And this will be less than or equal to pi over 2 C to the 3. So let me leave the pi over 2 here. So that means C will be greater than or equal to this number of the cubic root. Mm-hmm. Okay? So now the second one to meet the phi less than or equal to 1.5 degrees. So this is the second criteria we're going to check. And this one, again, the phi equal to D relative to C plus VC. And this one actually is the angle of the twist of the shaft CD. So TL over GJ for shaft CD. Okay, so this one is pretty straightforward. The T will be TCD is equal to 1,000, and L, for our calculation, L is 0.6 meter, and G is given, and J basically is pi over 2 divided by C to the fourth power, leaving C there. Okay, so here this will be the function of C, and C we're going to solve. And what is VC? And let me continue here. what is this one? Again, phi c represent is the angle of rotation at this end of the shaft, which means represent is the angle of rotation of this gear. So which can be related to this gear. So that come up with another information that is to complete the whole. So this is the top gear, and this is the lower gear. So this is RC, this is RB. So this is the contact point. So for example, if they're rotating in this direction, so that means at the time moment, the contact point will be moving to here, this will be moving to here, the arc length will be equal. The arc length must be equal, so that means here we determine this is the phi c, and this is phi b. So therefore, phi c multiplied with RC will be equal to phi b times RB. Okay, so therefore here the phi c equal to phi b, and that is RB RC. Okay, so this is the second portion of the compatibility equation for the gears. This is the first one. So with this case, for this problems, we can write it up into this. So basically that is RB equal to 40, RB equal to 100, and RC equal to 40, and this is phi b. What is phi b? Phi b represent is the angle of rotation of the gear. The gear solidly welded to the shaft. So phi b actually represent is the angle of rotation at this end. Angle of rotation phi b equal to phi b raised to a and plus a. This is the angle of rotation. This is what we call the twist angle. And A is fixed against the wall. So basically phi b represent is actually is our twist angle in shaft AB. Okay? This is called the angle of rotation. This is called the twist angle. Okay, or angle of the twist. So in this way, this will be equal to 100 multiplied here. And then phi b, that's a TL over GJ. And for shaft AB. So here the T in AB equal to 2500. And L equal to the length of the L equal to 0.4 meters. And J equal to pi over 2 times T to the fourth power. And again, the C appeared. So we plug in the information carefully here. So we have this one being formulated and this one formulated. So this one, basically here, if I plug in all the numbers, allow me, that would be equal to 31 divided by GJ, and this one less than or equal to 1.5 degrees. And remember here we must using the radian. So the radian basically is equal to 0.0026 radian. Okay, we use this one to calculate. So let me continue to here.
Could you explain your jump from the finding PC to over the other equation?
From here to here.
Well, no, you went from working down that sequence all the way to the bottom of that sequence, and then you jumped over to this other point.
Yes. So this is TC. This is TC, right? Because in this equation, this can be calculated by this relation. And because VA, the A is fixed against the wall. So basically, this one, phi b, actually equal to the angle of the twist in shaft AB. So here I plug in the angle of the twist in here. And then we keep the duration here.
I understand that.
Okay.
But, so you didn't come out with any number, and then you jumped over to this other side. You started
This one?
Yes.
Okay.
So
Yes.
3100, that's...
Yes, yes.
That's
Let me do this one. For example, here the phi b for shaft CD. For shaft AB. Okay. So basically, we simply plug in the GJ, and T is 1,000 times 0.6 plus 2.5 GJ 25 times 0.4. So we implement those things together, so this will be equal to GJ 3100. Okay, so we confine this one less than 1.5 degrees, so that is 0.026 radian. So which is 1.5 degrees. Okay? So in this way, the calculation, the C, using this way, C must be greater than or equal to 31.46 millimeters. Okay, so here we have two numbers. This is the second criteria, and that is the first criteria. So we have to choose the which one? That one. Okay, so this is our final answer.
Can you go over the criteria?
Yeah, this one is to meet the first criterion, and that one to meet the second criterion. So that means if we go that direction, if we choose that range will automatically satisfy this requirement.
Okay, yeah.
Right? I'm okay? So here we basically repeatedly apply the compatibility equations to and let me move on to if you know if you're a fan of the cars, and sometimes you go to buy, for example, once you build up your career, then probably you're going to reward yourself with a better car. So basically, you go to some specification, for example, the torque or the power, how many 150, I think 150, 145 horsepower is a very good, decent car. You can speed up, say, to 100 miles per hour in 10 seconds, and then you get tickets right away, right? So we talk about the power. What is the power that means? And basically the power equal to, right now we have run the shaft, 2 pi f t. T is the torsion or the torque we learned. T is the torque and application, so that is the one being calculated. And F is the rotation, speed of rotation of the shaft, and that is we call the rotation speed, and that is in hertz. Okay, so simply P is the power. So as long as we added up the additional information about the rotation of the speed of the shaft, then pretty much from here you can estimate the power of for example, your cars. So for example, each car, the output of the engine is if you know the engine basically is the assembly of a certain number of the piston. And each piston basically do the repeated motion like this. In the way one stroke, they will produce the torque. The output of the engine linking to a shaft and go to the transmitted from this kind of motion in the cylinder get into the rotation, the output. This torque basically determined by the engine, the size of the engine. Okay, but through the gear system design, you might be able to modulate. Not you, the car vendors may be able to modulate the frequencies. Okay, so kind of give you the information. This is the only other quick information. It's not that difficult, but it's kind of straightforward. So once we have all the information with the additional things, we can calculate. And this page is for the final topic. So I think Friday I will spend a little bit more time on this chapter and to catch up. But here, this is the very last topic about the stress concentration like we have. Again, the stress concentration will always occur on the discontinuity of the geometry. If from the smaller shaft to the larger one, then the stress concentration will happen at the connection link. We try to reduce and this kind of the stress concentration by using some kind of the fillet or some kind of the curve to curve the sudden change in the geometry. So here we have the similar curve like this. To calculate, and again, we can estimate the stress concentration factor K, and that is to this curve. And using the information is R over D. What is R? R is the radius of this curve of hook of the fillet. And divided by the D and the smaller case D. And the other one is these parameters, the ratio between the two shafts. Determine the K, and then we simply plug into this formula to help us to estimate the maximum stress. Okay. So this one will give us another design criteria, and then again Friday coming back, I will spend a little bit more, a few more minutes and talk about one example about this. Okay, and then probably you can finish all the